So now I'm going to talk about publication bias. This is closely related to p-hacking, and it's another way in which scientists can unknowingly bias their own results. The basic idea is this: any experiment you do, a survey, any research is going to have error bars, uncertainties, which means that the final result you get might be bigger or smaller than than the true value. Now, in principle, that's fine. Some results are going to have bigger, some papers are going to have smaller. If you average them all, go through the entire literature, you should get the right answer on average. The trouble is, what happens if not all these results are published? So let's pick an example. Let's imagine that we've got 100 educators and they've come up with this new idea, this new technique, and they think it's going to be wonderful, it's going to improve education for our primary school students, help them read and write better. Doesn't matter what it is. So these 100 people get funding and go out and do surveys to see whether indeed this method makes things better or not. But let's imagine this method, whatever it is, actually makes no difference. It doesn't improve or hurt learning. What's going to happen is, of these 100 different surveys, 5 on average will find that it improves learning with a statistical significance of 0.05. So it's going to be 95% confident that it improves learning. Another 5 are going to show that it makes reading worse with the same confidence, and 90 are going to find nothing statistically significant. So far, so good. If you average all those 100 surveys, it's giving you the correct answer, which is no effect. The trouble is, a lot of those surveys are not going to get published. Bear in mind that the researchers got into this because they want to make things better for students. They want to find a new method that's going to improve student learning. So the 5 people who find that this made things better, they're going to publish their papers. They're going to publish papers saying, look, we've tried out this new method and it made things better with 95% confidence, P of 0.05. How about the people who find nothing significant? Are they going to publish? Publishing a paper takes a lot of work and usually costs money and takes time and is often quite painful. It'll be hard to get something like this published. It's not going to help you very much. A paper saying, we tried this and we didn't find any important result, but maybe it's worth trying again, la-di-da, la-di-da. Not very interesting at all. How about the 5 that find it made reading worse? I mean, they might publish. Hopefully they should publish and say, don't try this, it's going to make things worse. But again, the whole reason they're in this game is because they want to make things better for students. Why go to the effort of publishing something that doesn't make things better for students? No one's going to benefit from it. So what you only get is these 5 published. Maybe 1 or 2 of these. There might end up being, 8 papers, 5 of which make things better, 2 of which find no difference, and 1 of which makes it worse. So if someone comes along after the event and surveys the entire literature, they'll find overwhelming evidence that this technique works. They'll go out and tell all the teachers to do this. Now there's a way to analyse these things which is called funnel plots, which is widely used. The basic idea is you plot along the bottom the strength of your measurement, which might be how good your education innovation is, or it could be you're trying to, measure the power of a new laser or something like that. And so you have a very powerful laser, a very weak laser, a very good intervention, a very weak intervention. Vertically, we've got the power of the survey. This is how accurate the survey is. A high power survey has a small uncertainty, whereas a low power survey has a big uncertainty. Now remember that making your study better is always going to cost money and time. So for example, if you wanted to do a survey of 10,000 students with double-blind randomized control survey, that's going to cost a lot of time and take probably years of work, but it'll get a very accurate result. Whereas a very quick and dirty survey of 20 students in my class and 20 students in a neighbour's class is quick and easy to do, but we'll get a much more uncertain result. Likewise, if you're trying to measure the power of a laser, doing it very accurately might require expensive equipment and lots of painstaking time in the lab, whereas getting a quick and dirty answer might be very easy. So you always find this trend that there are going to be low power, high uncertainty measurements, and they have a big scatter. Sometimes they're going to show bigger results than the true value, sometimes lower. But then the funnel's going to narrow as you go up. The more and more powerful studies, which are also the expensive and time-consuming ones, they'll get closer to the true value. So this is what you should see. And if you average over all this, you're going to get a decent average. But that's not what you typically see. Remember that the first studies of anything are usually going to be the low power ones. If you've got a totally new idea that no one's done anything before, you're probably going to do a quick and dirty easy survey just to see if it works. And if it works, you might then go and you've got evidence to apply for grant money to get a bigger survey going. It's going to cost money and take time. So the initial results are going to have a lot of uncertainty. Some are going to be bigger and some are smaller than the true value. Now, which of these get published? If you're looking for something, you discover something bigger and more interesting, you're going to publish. You're going to publish in a big major journal. Whereas if you find a small, less interesting result, maybe you publish, maybe you don't. It's not going to be very interesting, but you're certainly not going to follow it up. So the low power, high uncertainty initial surveys, nearly always the published ones, show really strong results. And these are the ones that get followed up. And what you're going to see is as you then do bigger and bigger surveys, they're going to get closer and closer to the true value. And so you'll see this sort of curve. And this you see over and over again. The first studies in a field show a really exciting result but have big uncertainties, and then follow up, find a smaller and smaller result. I've done this myself. I was doing a survey for clustering of galaxies in the early universe, and our very first result showed really strong clustering, far stronger than any theory had predicted. So I published the paper. It was a well-cited paper. It was very exciting in a good journal. That meant that I was able to get funding and telescope time to follow this up to see if more people could find the same result, and other people did the same thing. And it turns out that I was right. The clustering of the early universe is much stronger than the theory predicted, but it's not as strong as my first result showed. People found in the end there was a strong signal, but not as strong as the first results. So that's what happened. You often see this trend. Initial results show something really exciting, follow-up show it's still real, but not as big as the first result showed. This has two problems. One problem is the research down here is missing. This is where you did your first low power survey and it was boring and you didn't publish it. It just stayed filed in your desk drawer. What happens if my first result had been like this? I did a survey of clustering the universe and discovered nothing very interesting. I probably would never have followed it up. So first of all, we could be missing a lot of results because we do the initial survey and it shows something not very interesting. It either doesn't get published or gets published in an obscure journal and no one bothers following it up. So that's one problem. There could be all sorts of interesting scientific results that were never discovered because that first noisy observation came up with this bad result. In some sense, it might be good that people didn't publish the first result because if they had published, other people might have not bothered doing it again. Whereas if you don't publish, there may be someone else that doesn't realise you've done it and might get a higher result. The second problem, though, is that if you average all of these results, especially if there are only low power results, you're going to get a much higher result than you should. So a meta-analysis, a literature review, is always going to give you too strong an answer. And this is indeed seen. People have generated lots of these funnel plots and they always see this trend where they're missing the low power, low result things and so forth. The average is crap. So it's very widespread. Most estimates are that of all the studies ever carried out, probably at least 50% are never published because they gave boring results and people couldn't be bothered publishing them. And therefore any survey of the literature is always going to be biased. What's a solution to this? Oh, I should mention, this is actually a biggest problem for the more prestigious journals, because the most prestigious journals like Nature and Science like to publish exciting, trendy, dramatic results. And these are going to be the results down here with the small surveys that gave a really big result. And so in fact most studies show that the prestigious journals have worse publication bias than the less prestigious journals and therefore actually have a worse reproducibility crisis. So being in a prestigious journal means you're more likely to be wrong because they only publish exciting results and exciting results are more likely to be statistical flukes. So solution. The obvious solution would be that everybody must publish their result whatever it comes out as. So this is the idea that we pre-register, that before you do a survey, you commit, I'm going to do this, I'm going to analyse it in this way. As we've already talked about, pre-registration commits you to a particular strategy for data to stop you harking and changing your hypothesis after the event, because they can look and say, here's what you said at the beginning, and you didn't do this, therefore we can't trust your result. So you specify ahead of time what your hypothesis is and how you're going to analyse it, so there's going to be no temptation to, it only came out as P of 0.07, maybe I'll tweak something here. And secondly, this hopefully commits you to publish. So even if you get a boring result, it publishes. So if someone surveys the entire literature, they will find that it gives us a good average. A tweak on this is actually to pre-approve publication. The idea being that you might submit your plan to the journal and they will say, well, this looks like a sensible plan. I'm going to guarantee we publish it whatever the result, as long as you actually do publish it. So this way makes it, because if you've got a sensible strategy, it's all worked properly, then you should get a good result, and they should publish whether it's giving an exciting result or a boring result. Of course, people may not read it if it's a boring result. So these can be done, and in psychology and medicine, a lot more of this is being done. It's not done so much in physics yet, which is maybe a mistake. Maybe we should be doing more of it.